So I decided to redo this again because I just want to make sure that projectile motion is something that you have as much comfort with as possible. It's a big part of this unit, and it's a big part of the AP test. So I keep looking at my screen because going, I don't like the way you did that, Eric. Let's try it again. So here I go, a third time's the charm. Sorry if you watched one of the other ones, but this one's going to be better. All right, let's get on it. Projectile motion. By the way, I'm at this really cool house. It's like 200-year-old house in overlooking the Hudson River in upstate New York. I'm here for my nephew's wedding, which is the best wedding I ever went to. But anyway, so that's why I kind of got this weird, like canopy bed behind me and whatever. Okay, and weird lighting in this old house. Okay, anyway, let's get going here. Projectile motion. So I said the most important thing you can remember about projectile motion is this: the horizontal. When I have an object that's traveling, it's launched upward, projected upwards at an angle. So it's no longer horizontal to the ground like the ones we looked at before. So, we talked about the independence of horizontal and vertical motion, but in this case, it's at an angle. What that means, if it's moving this way, it's both moving horizontally and vertically. So it has components of each. So what we'll learn to do is take this velocity at a certain angle and resolve it into a horizontal and vertical components, or maybe we'll be told what those are. And the thing to keep in mind is the horizontal component isn't going to change over time. We've talked about this. There's no force causing acceleration in the horizontal direction, but there is gravitation causing acceleration in the downward direction. So what we'll find is that there is a change in the vertical velocity over time, but not in the horizontal. That's the big thing to keep in mind. So you need to know the vertical versus the horizontal. No, the horizontal stays constant. The vertical one is subjected to gravitational acceleration, and that informs you as to what equations to use. So let's just try this one here. So I got an object. We determined that it's got, it's shot this way. So it's got 30 meters per second of upward velocity and a vertical velocity, and it's got 20 meters per second horizontal velocity. So what's going to happen is the 20 meters per second is never going to change. It's always going to be moving 20 meters per second in the horizontal direction for the full time it's in the air. But that's not true for the vertical. So the vertical velocity is subject to gravitational acceleration. Remember, the gravitational acceleration vector points down, and in this case, the initial velocity vector is pointing up. So when the velocity vector and the acceleration vector are pointing in opposite directions, you're going to slow down. And when they're pointing in the same direction, you're going to speed up. So what we find is once it comes out with a vertical velocity of 30, a second later, it's 20 because it lost 10 every second. A second later, it's 10. A second later, it's 0. Still moving though, but it's not moving vertically anymore. Now it's going to start picking up speed since the velocity vector and the acceleration vector are both pointing in the negative direction. It's a second later, it's going negative 10, then it's going negative 20, then it's negative 30. And yet that whole time, through that 6 seconds of flight, it was always traveling 20 meters per second horizontally. So let's try drawing motion graphs to see if we can, really wrap our head around this. Okay, so let's try this. Let's start off with a velocity graphs for the two of them. Okay. So let's do the vertical velocity. So the vertical velocity starts off 30 meters in the positive direction. So I have positive 30, and it's going to diminish 10 meters per second every second. So I'm going to get a negative slope of 10 meters per second. So remember, the slope of a velocity graph is going to be acceleration. I should get a negative slope here, and I should reach a velocity of 0 at the apex after 3 seconds, after which it's now speeding up in the negative direction. So it's slowing down in the positive direction, reaches 0, then it speeds up in the negative direction. Meanwhile, the horizontal velocity stayed 20 the whole time, so it never changed. Okay, let's take a look at acceleration then. Okay, well, so if I do acceleration, what I should find is in the vertical component, I should have negative 10 meters per second squared the whole time. The entire duration of flight, it had an acceleration of negative 10 g. However, the horizontal motion, because we're going to discount any kind of acceleration caused by drag or air friction, whatever we want to call it. So it's got an acceleration of 0 the whole time. Now let's try position. Now, be a little bit careful with this one. I know if you were to watch this arrow be shot in the air, it would look like that. But in that case, what this would be is the horizontal displacement. This would be the vertical displacement, or position rather. But that's not what we're looking at. This is time, okay? And so we see the vertical motion. If I just do something straight up and it came down, this is what we'd see. We got a frown. It's got negative acceleration. I start off with remember, in a position versus time graph, the slope is the velocity, right? So I see I have a high velocity here, 30 meters per second, and then 20, and then 10, and now it's flat. It's got 0. Now it's negative 10, negative 20, negative 30, if I was to take those slopes. If I look at horizontal velocity, the slope should never change because the velocity never changed. So I get a slope of 20 meters per second throughout the entirety of its time in the air. And now let's move on and look at this here. We often want to talk about the speed of an object, and the speed is a scalar quantity, but it's something that's it's worth noting when you're talking about a projectile motion, because if you're moving both horizontally and vertically. But if I want to talk about how fast you're actually going, if you were in a jet aircraft that had a 20 meter per second, it's not very fast for a jet, but 20 meter per second horizontal velocity and a 30 meter per second vertical velocity, what would your airspeed reading be on your jet? Well, so I basically what I do is I would add these two vectors using the tip to tail method, right? Doesn't matter which one I do first. And then remember to find the resultant. You start at the beginning, you end at the ending. Even though what I'm really getting here, I mean, it could give me a vector if I want to assign a direction to it. Or I could also just get the magnitude of it and call it the speed. And I'm just going to use Pythagorean theorem. I'm going to say 20 squared plus 30 squared, take the square root. I get 36 meters per second. So that's how fast it's actually moving. And this is how fast it's moving horizontally versus how fast it's moving vertically. So sometimes we need to do that to like reconstruct what the magnitude of its velocity or speed is. All right. Now, if I graph that, that was kind of an interesting, and College Board does like to ask this question. Here's why. A misconception students often have is at the apex of the flight, it stops moving. That'd be true if it had no horizontal component, but just throw something up. Yes, at the apex of, if I toss a ball in the air at the apex, it's got a velocity of 0, right? But now it's moving horizontally at the same time. So what I see is if I was to take those two components and calculate, if I say, square root of 20 was square root of 30 and take the square root, I get 36. So I start there. I'm going to begin and end at 36 because it's a scalar. So I'm not keeping the positive and negatives in mind. But what I find is the main thing to keep in mind here is the speed is going to diminish because now it's 20 squared plus 20 squared, take the square root. Now it's 20 squared plus 10 squared, take the square root. Now it's just 20. And so there's a minimum. And the point is that the minimum speed it's going to have in its flight is the horizontal velocity, and it will have that value at the apex. So they often ask questions to see if you're going to remember that at the apex of a ballistic trajectory, you still have a speed there. Okay. Now, this is a really important skill here. Unfortunately, it's quite straightforward, and that is that if I know the launch velocity is, say, 50 meters per second, I know the launch angle is 60. Well, then what are the vertical and horizontal components of that going to be? And so we just got to remember SOHCAHTOA. Okay, so if I think about this as a triangle, so here's my angle. So this would be, remember, so means sine uh, opposite over hypotenuse. Okay, so if I want to find the opposite value, I say this times the sine of this. So to find the vertical component velocity, which is going to be the opposite one, because we're usually given the launch angle relative to the ground, I take this launch speed or launch velocity, and I multiply it by the sine of the launch angle. Make sure you're in degrees and not radians on your calculator when you do this. And therefore, if I want to find the horizontal, remember you have so ca. So remember, ca is cosine is adjacent over hypotenuse. So the adjacent, which is the horizontal, is found using the cosine. So I take the launch speed here, and I just say 50 meters per second times the cosine of 60, and that's going to give me the horizontal component velocity, which in this case would be 25. And when I take 50 sine 60, I get 43.3. So I can, given this information, I should be able to, and you should be able to determine what the horizontal and vertical components are going to be. Right? There's sine for vertical, cosine for horizontal. And every once in a while, we're asked to do the opposite. We're given the horizontal vertical components. We're asked to know what angle is launched at. And so let's just keep going with this. So TOA. The TOA means tangent is opposite over adjacent. Okay. So if I was given these two values here, I would say, well, to find this angle here, I would say the tangent of this angle is equal to opposite over adjacent. But I don't want to know what the tangent of it. I want to know what the actual angle is. So then what I do is I have to take the inverse tangent of both sides. So the inverse tangent of 30 over 20 gives me a value of 56 degrees. And that should look right, because if these were both the same, that'd be a 45-degree angle. And since the vertical is more than that, I should have more than 45, which is what I got. So I know I did it right. Okay, keep going here. All right. So when we're given these problems, these ballistic problems or projectile problems, projectile motion problems, We have to first thing to keep in mind is if I want to know the horizontal value, I have to take the cosine of the launch velocity times I take the cosine of the angle times the launch velocity. So I know this velocity v, so v cosine theta, that's going to give me the horizontal velocity, the horizontal component of velocity. And if I want to know displacement, which is often what I want to know, like how far away is this thing going to land, I take this equation here, the one that does not involve acceleration. I'm going to rearrange it for delta x. So that means normally v times delta t. But in this case, it's going to be v cosine theta, because if this is v, this part over here is going to be v cosine theta. Okay. But if I want to know like how long it's in the air, that's a little bit different, because if I want to find the horizontal distance, I've got to know the time. The time, keep in mind, is always determined by the vertical aspect of its motion. In this case of projectile motion, you take you need to find the vertical component of velocity, because that's going to tell you how long it's in the air. The faster it's moving upwards, the longer it's going to get to stay in the air, and the farther it's going to get to travel horizontally. So here's how we're going to do this. We say, well, let's launch it at velocity v at angle theta. So the vertical component is going to be v sine theta. All right. Now, if I want to figure out how long it's in the air, think this through here. It's a little bit tricky. You got to keep in mind that we're gonna say down is negative and up is positive. And, usually we say set the initial direction of motion as positive. That's up. So that means then that the initial velocity vi is going to be v sine theta. But the final velocity, it's moving in the downward direction, so that's going to be negative v sine theta. It's going to be having the same magnitude, but in the opposite direction. And you also have to remember the acceleration, which is g, 10, is in the downward direction. There's got to be negative g, or negative 10. So if I want to find the time it's in the air, it's going to be negative v sine theta, that's the final, minus the initial, which was v sine theta, over negative g, which is also in the negative direction. It seems a little tricky, but I'm going to show you a shortcut, okay? And when I do that, the negatives cancel out, and this becomes negative 2v sine theta over negative g, or 2v sine theta over g. It's how long it's going to be in the air. So let's just say that when I took v sine theta, what I came up with was 30 meters per second. How long is it going to be in the air? Well, according to this, it would be 30 times 2, that's 60, divided by 10, that's 6. But there's a quicker way of doing it that I like to do, which I just do this. I say, okay, if I know that v sine theta, the vertical component, is 30, I just go, look, if it's going up at 30, I'm going to divide by 10. It's going to go up for 3 seconds. Now it's got to come down. That's another 3 seconds. So I just take the vertical velocity, divide it by 10, and double it, because it's got to go up and it's got to come down. So I like to do that because I don't have to worry about all the negative directions here. It's easy to screw that up, but for me, it's really easy to say, like, if you shot up at 35 meters per second, it's going to go up for 3.5. It's going to go down for 3.5. It's in the air for 7 seconds. That's how I approach that. Okay. So let's try this one here. Let's just read the prompt. It says soccer ball leaves the ground with a vertical component of velocity of 25 meters per second. And it lands 60 meters away. What was the horizontal component of the ball's velocity? So the first thing I got to keep in mind is, remember, horizontal velocity has no acceleration. So this is the equation I have to use. V equals delta x over t. There is acceleration in the vertical direction. So I'm going to use this one here. I'm going to use acceleration equals delta f over delta v over delta t. All right. So the easy way, I'd say, well, 25 divided by 10 is 2.5 times 2 is 5. Or if I want to be more, I suppose I want to just keep with my kinematics equation because I feel safest that way, I would rearrange this equation for delta t. So that would be delta t equals vf minus vi over a. Keep in mind a is negative 10. Keep in mind that the 25 was the vi, so vf would be negative 25. So negative 25 minus 25 is negative 50, divided by negative 10 is 5. So the other way is a little bit quicker, but this is safer, I suppose, in a way. Okay. What's the vertical component of horizontal component of velocity? Well, it's going to be the horizontal distance traveled by the time. So it travels 60 meters. So I'm just going to use this one here. I'm going to say, well, delta x was 60 meters, delta t was 5 seconds. So therefore, the vertical component of velocity was 12 meters per second. And if I want to now, I could find out what the launch angle was by doing inverse tan to try to do that. Okay, let's keep going here. All right, how about this? An arrow is fired at 60 meters per second. So it comes out of the bow at 60 meters per second at an angle of 30 degrees above horizontal, how far away is it going to land? A classic question. You're going to get good at this. So the first thing I'm going to do is I'm going to divide up the horizontal and vertical components. Well, so I keep scratching this little surgical scar. Ooh, look at that. It looks like I look like Harry Potter. I got this zigzag scar here. Okay. So the vertical component is, remember, it's going to be sine theta. So I'm going to say launch velocity 60 times sine of 30. Remember, I got to be in degrees on my calculator. It's going to give me, well, since the sine of 30 is 0.5, it's going to give me 30 meters per second. The horizontal component velocity is going to be 60 times the cosine of the angle 30. And that's going to give me 51.96 meters per second. So it's moving a lot faster horizontally than it is vertically, which makes sense because I'm shooting it, closer to horizontal than I am to vertical. I wonder how far away it lands then. Okay, I'm sorry. So now that I have this, I've got to figure out how long it's in the air. Well, using my technique, I'm going to say, well, 30 divided by g, which is 10, is 3 times 2, because it's got to come back down, is 6. Boom. If you're using kinematic equations, you set it up this way. I'm using this equation. I'm going to switch it around. So I'm solving it for delta t. I have to remember that a is going to be negative 10. That VF is going to be the negative of this because it's going to be coming down at 30. So minus 30 minus the initial velocity, which was 30. So negative 30 minus 30 is negative 60 divided by negative 10 gives me 6. Either way, okay? Now I know it's in the air for 6 seconds, so how far is it going to travel in those 6 seconds? Well, it's traveling horizontally at 60 cosine 30, or 51.96. So this times the time it's in the air is going to give me how far away it lands. A couple things to keep in mind. And one is that for every angle that puts a projectile at a particular distance, there's another angle that'll do it as well. Okay, so let's just say I shoot something at 15 degrees and it lands here about 500 meters away. Uh, if I shoot it a little bit higher up at 30 degrees, it's going to go further. If I shoot it at 45, it's going to go the farthest. So it's worth noting that the farthest it's going to go is when you shoot at a 45-degree angle, if it's landing at the same level it left from. We'll talk about that in a second. But if I shoot at more than 45, it's in the air longer, has more hang time, if you will. It has a higher vertical component velocity, so it's in the air longer, but it's traveling less, it's slower horizontally. So even though it's in the air longer, since it's traveling slower horizontally, it doesn't go very far. I think if you shoot it straight up, it's horizontal velocity 0, it's not going anywhere, right? So what I find is after 45, it starts going less and less distance. And interestingly, and it makes sense when you think about it, for every angle that puts it a certain distance, there's another angle that puts it there as well. And here's how you would find that. So let's just say, let's go with 45 goes the furthest. But if I shot it at 30, it would only go to here, right? Well, so basically 30 is, so basically if you say 90 minus 30, what do you get? You get 60. So 60 would also send it in the same direction. Why? Well, because 60 is 15 above 45, right? And 30 is 15 below 45. And they're going to put it the same distance. If 15 degrees sent it here, 90 minus 15 is 75. 75 will also put it the same distance. And again, it's because they're the same number of degrees away from 45. But it's worth noting that there's going to be two angles that put it in the same place. They like to ask that question of you. Now, here's the thing, though. One time they've asked this question, and this is a hard one. I don't want to get into it. But if I'm shooting off a cliff rather than onto level ground, which is usually the case, then it turns out that 45 is not going to be the one that always sends the furthest distance. If it falls a certain distance, and it usually has to be quite a bit, then what happens is shooting at a lower angle, even say 0, could send it further. So if it fell 300 meters and I fire this one at 0 and this one at 45, they land different distances, and the 45 wasn't the furthest. Now, this is kind of an esoteric aspect of it, but they have asked this before. Okay, so let's just try this one now. Okay, so what if we just try to do it without numbers? Okay, so we say when a ball leaves the ground at speed s at angle theta, it's in the air for time t and lands horizontal distance delta x away. Okay, so if it left the ground at the same angle theta but at 2s, how far away would it land? And your instinct might say twice as far, but hang on a second. if I double this, then that means I've doubled both the horizontal and vertical components. Try yourself and see it's true. Okay. So that means then that the distance it travels horizontally is equal to v times t, but because it's, if let's just say it was 30, okay? So if it went for 30, it would go up for 3 and down for 3, it'd be in the air 6 seconds. But if I shot it double that, 60, it'd go up for 6 and down for 6, and that's 12 seconds, right? So when I double the vertical velocity, I double the amount of time it was in the air. Same is going to be true for the horizontal. I'm going to double the horizontal velocity. So if this is 2t and this is 2v, then the horizontal distance I get is actually 4 times greater. Kind of an interesting one there. Okay, that's it. Thanks. I'm sorry this is a little bit long, but I think it's better than the ones I did before. I didn't get into a lot of the more math of parabolas because really College Board doesn't ever ask about that. So hopefully this works for you. Thanks for watching, and I'll see you guys next week.